Good afternoon to all of you. Before we are going to start, I would like to welcome all of you in the virtual platform provided by IGNU for the counseling of the course BMTC 131 Calculus. Let us see in BMTC 131 Calculus, the first block contains exactly 5 units. So let me to share the PDF of it. As you can see here, if the counseling of BMTC 131, which is about calculus, and in block 1, we have to cover the essential, basic, preliminaries over set theory and function, complex number, etc. So in block 1, exactly we have 5 units. In unit number 1, we have to cover sets and operation on them. Unit 2 contains all about functions. Unit 3 contains two-dimensional geometrical systems. Unit 4 is all about the complex numbers. And finally, in the first and final unit, we have to cover polynomial equations and their solutions. So let us begin with the first unit, that is all about the sets and its operations. So in the first module, we have to cover all about the sets, subsets, Venn diagrams, operation on sets like union, intersection, implementation, and Cartesian product. And then we have to cover the law on operations, just like distributive laws, associative laws, commutative laws, and De Morgan's laws. And finally, some summary of this particular chapter. Let us see, and as we know about the set theory from the school level, and it is very much well known to us all the definitions and notations about sets and their properties. So I'm going for a quick review about sets and its operations. Generally, a set can be defined in simple way, that is a well-defined collection of object is called a set. So here, let us look at the word well-defined, which is clearly known to us. And when the objects are clearly well-defined, then these objects can make a set, and the set will be represented by a curly bracket, a set of curly bracket, left curly bracket and right curly bracket. And as you know, we have standard set notation. These are capital N is reserved for the set of natural numbers. Capital Z is reserved for set of integers, and Q similarly reserved to denote the set of rational numbers. And similarly, finally, capital R is also reserved to represent a set containing all of real numbers. So let us see a set, and generally all the elements of a set are represented inside a curly bracket, and all the elements are represented within the separated by commas. And generally, we have two different methods to represent a set. First one is listing method, tabular method, or roster method. Second method is known as set Wheeler form. or it is also known as property method. So generally, in set builder method, we are not going to represent each and every element inside the set, but we are using certain variables. Instead of this particular element, we are using certain variables to represent that particular set. So that's why it is known as a property method or a set builder method. So generally, we form a particular form of property to represent a certain kind of set in the form of certain notations and representation in the form of a property of set builder method. Now let us see an example. So here some property examples of property method or set builder method is given here. So let us take an example of a set capital E, that is a set of all natural numbers which are strictly less than 10. So here if we are going to list all the elements of the set E, then the elements will be here 1, 2, 3, 4 up to 9, because you have the condition given x is strictly less than 10. So the elements will be 1 to 9. So this is the second form of representation, and this particular form of representation is very much important in our future calculations or future calculation. So now let us discuss about the equality of sets. That means under which condition we can say that two sets are equal. So here, if the elements of the sets are exactly same, that means the number of the elements are exactly same as well as the elements are itself in similar form, then we can say that yes, both the sets are equal. And we can write also A equal to B or S set equal to T set. But generally, in practice, when you are going to list all the elements in a set, elements are not repeated more than once. If any one element is repeated more than one, then when we are going to calculate the cardinality of the set, we are not counting an element more than one time, or we are not going to repeat the same element in our calculation. Now, finite set and infinite set. So here, a finite set is a set which contains exactly a finite number of elements. That means this finite number of elements is the number. That number denotes the cardinality of a set and represented by a vertical lines, or we can write also CART, cardinality of A. If an set containing exactly one element, that type of sets are known as singleton set. So these are the some basics of sets and its notations. And if an element is present inside a set, then we can represent 1 belongs to n, set of natural number n, or 2 belongs to set of natural number n. That means we are using a symbol belongs to. Or we can write also, we can say also x in n or 1 in n, like that. Now let us moving towards the subsets. So here in subsets we must have exactly two sets. If all the elements of the certain sets are entirely lies in the in other set, then the first set is known as the subset of the second set, and we are using this symbol in the form of just like C. We, we can give equal sign in the lower bar, and here we can also say A contained in B. A is a subset of B is also can be represented in the form of A contained in B or B contains A, or can denoted by B superset A. We can read as B superset A, or also can say that B contains A. So here, if a set capital A is a proper subset of B, then we can represent like that A proper subset, that means not equal to, so here not equal to B. The only differentiation is that A is proper subset of B. So now let us see about the empty set. So empty set is a set that does not contains any element in it, and empty set is a subset of every set. So here it can be written like that phi. So generally empty set is represented by using the notation phi. And we are using the symbol of representation like that. Phi, phi is a subset of A. Now look at the notation implies and implies phi, or it is equivalent to, or we can say that by implication, or it is also known as double implication. So now for a better grip in set theory, we are using Venn diagram to represent different sets and its operations. And generally, this Venn diagram is very useful when we are discussing sets and its sets operations. So generally, we are using capital U is a universal set in set theory, and all other capital alphabets like capital A, capital B, C, D are used to represent a set which are coming under the universal set U. So let us now discuss about the operation of sets using this Venn diagram. So here, first operation is union. So union is represented by A. So first is complementation. So complement of a set. If a set capital A over an universal set U, then we can represent complement of A in B. Complement of A in B denoted by B minus A, or B complement A. So here we can represent A difference B, or A minus B denoted by A belongs to A, such that A does not belongs to A. And this particular idea can be represented in the form of A complement, that means A to the power C, or A prime. We can represent A prime or A complement is the complement of the set itself. It can also be denoted as A complement equals to U difference A, or U minus A. So here basic idea is that when X in A complement, it meaning is that A X does not belongs to in the set A. Now let us look at the definition of mutual disjoint sets. So let capital A and B are two sets such that A intersection B equals to phi. Then clearly you can say that both the sets are mutually disjoint set. And the same can be observed in the figure, which is represented in the set A, B, C, and clearly their intersection or some elements are common in the set A and C, but B is not intersect with A or C. That means you can write here A intersection B equals to phi, and both the sets A and B are disjoint sets. Now the laws of distributive property. So here generally or basically we have two laws of distributive property. Now for distributive property we have to consider three non-empty sets, capital A, capital B, and capital C, over or over a universal set, an universal set capital U, and it can be represented. The first property can be represented like that: A intersection B union C, that is equals to A intersection B union A intersection C, A intersection C, and that is, you can say that intersection is distributive over the union. Similarly, the second property can also be represented that A union B intersection C, and it can also be represented like that: A union B intersection A union C. So here the bracket are given in the first pair and second pair, A union B and A union C. and intersection is lies in between. So here you can say that union distributes over the intersection. And this is a simple proof. Let us see a simple proof. And this basic idea is based on the equality of sets. So here, to prove this certain result, we have to approach in the form of the first set is a subset of the second set. And again, if the second set is a subset of first set, then by combining these two sets, we can write that the first set must be equal to the second set. And that can be done considering some elements lies in the left set of the first set, that is A intersection B union C. So that's why we have taken here X belongs to A intersection B union C, and according to the property of intersection, we can write here X belongs to capital A, and because of this intersection we have to represent here and X belongs to B union C, and that can be later on we can express in the form of X union B or X union C. And finally, we can use here the property in the form of distributive law. So x in A and x in B, or we can represent x in A and x in C. Now, if we are taking common x, then it is the definition of intersection A and B, and second pair is the definition of intersection of A and C. So we can represent here x in A intersection B or x in A intersection C. And finally, we can combine these two results by union, because or can be replaced by union, and it can be represented like that x in A intersection B union A intersection C. And clearly there is a right hand side of the set. So we are starting from the left hand side, we are approaching towards the right hand side. So clearly here the first set in the left hand side is a subset of the right hand side. And similarly, by going upward, we can also show that the right hand side of the set is a subset of the left hand side of the set, and both the expression or the analysis can be represented in double implication symbol, just written in the final version of here. And finally, as you can see that now this is two-way implication. So if we are using two-way implication, then we have to represent only the one-way expression, this one. Finally, we can conclude that both the sets LHS and RHS both are equals, and the same has been represented in the form of Venn diagram, and that is the Venn diagram of A intersection B union C, and that is same as to say A intersection B union A intersection C. In the same way, we can prove the other result of the distributive law. In that case, that union is distributive over intersection. Now let us see about the Cartesian product. So Cartesian product can be represented by a cross symbol. So here we can represent A union B cross C, and that is equals to A cross C. That means A Cartesian product C union B Cartesian product C. And here we can say that in language the Cartesian product of set distributives over the set of union, and the procedure to prove are exactly the same process we discussed earlier in the distributive law. Now let us discuss about the De Morgan's law. In De Morgan's law, we are just using the complement of a set. Generally, or basically, we have two De Morgan's law. First one is for intersection. That means it is different here. Complement of A intersection B equals to union of complement of A and B sets, and symbolically we can represent in the form of complement of A intersection B has been written here complement of A union complement of B. Similarly, the second one can also be represented like this: complement of A union B equals to A complement intersection B complement. And we are using the same approach or same ideology or same basic idea to prove the same result in De Morgan's, just like that. X in complement of intersection B that can be expressed in the form like that: X does not in the intersection of A and B. And according to the definition of intersection, we can express in the form of X does not in A. Now intersection will be now here or, because of this does not belongs to symbol. So here or X not in B. And finally arriving a situation of X in A complement union B complement. So here as we can approach from left to right or right to left. That means 2A implementations are there, and we can represent here left hand side set here right hand subset of right hand side. So we can conclude here the left hand side set must be equals to the right hand side sets. And here are some results. So this is a summary of unit number 1, that is all about the sets and its operation. So let us look about the second unit. In second unit, all the basics about functions are given. Now with the second unit, second unit is totally dedicated to the function chapter. And here first we have to begin with the relations, and then relations is in the form of functions. Then we have to discuss the composition of functions, then binary operations, and finally the summary of all the relational functions and composition of functions. So let us see, let us begin the definition of a relation over two sets. And generally, whenever we want to define a relation over two sets, it can be represented by capital R, and the elements of the relations will be represented in the form of order tail, that is by using the parenthesis. The first element represents x, comma y, second element is y, and it can be represented x, comma y in n cross n. So here the relation is defined over the set of natural number n, or clearly you can say that capital R is a subset of partial product of natural number n. So with this basic idea, you can say that a relation is always a subset of partial product of a set or a pair of sets. And now, when a relation satisfies some particular conditions like reflexive, symmetric, and transitive, then that particular relations are known as equivalence relations. So let us see about the particular condition under which the relation is said to be a reflexive relation. So here in definition you can see we have taken a relation R that is defined on a non-empty set S. The relation in R is said to be a reflexive relation if this condition is satisfied. That means A is related to A. That means for each element A present in the set S, there must be the relation with its same elements. That means if A is in S, then AA must be in R. If the element B is in S, then there must be a pair BB in the relation R. So that's why it has been written that for every element present in the set A, this condition is satisfied. If this is true, then we can say that yes, the set R must be a reflexive relation. Now let us look at the second relation, that is symmetric relation. So here in symmetric relation, we have to represent like that A is related to B. That implies that B is also related to A. For all A and B lies in the set A, and that can be represented by using the form of parenthesis, that is A comma B in R. That implies if we can show that B and A is also in R, then finally we can give a conclusion that R is symmetric relation. Similarly, look at the third one. So here the third property is all about the transitive relation. So here we have three pair of elements, that is A is related to B and B is related to C. If these two given pair of relations are there in the relation R, then we have to find a relation that is A from C. Then if the relation is exists in the same relation R, then you can say that yes, the relation R is a transitive relation. And in order pair form, we can represent like that: A B in R and B C in R. Then A C must also be in R, or the relation R. Then yes, we can say that the relation R must be a transitive relation. So here some examples are given. So for the better grip of this relation chapter, the students are advised to go through the each and every examples given in the textbook. Now, look at the definition of equivalence relation. So as we have discussed here, when a particular relation R defined over a set S is called an equivalence relation if R is reflexive, symmetric, and transitive. If it is satisfied each and every relation, reflexive, symmetric, and transitive. So under this condition, we can say that yes, the relation R must be an equivalence relation. So now look at here in this definition of relation from x to y. Let x and y, capital Y, be two non-empty sets. So now we can say that a relation from x to y is a subset of the Cartesian product of both the non-empty sets, capital X and y. And the same idea will be now developed in the form of function to represent the function. So now we are going to know when and under which conditions a relation can be modified in the form of a function, or we can say that a relation is a function. So here, as you can see, the basic definition of function is, so here R prime. So here R dash or R prime is a relation over the set of Cartesian product of capital H and capital L. So now this particular relation R prime or R dash is said to be a function if these two conditions are satisfied. Condition number one is for each element x in H, there is at least one element y in the second set L such that the order pair x and y must be lies in the set R prime or R dash. Similarly, we can say that for each element x in S, there is only one element y in the second set A, such that we can say that the same x y order pair must be lies in the relation R prime or R dash. Under this condition, we can say that the relation R prime is an example of a function, or we can say that it is a function. So now with the basic idea, we can define the definition of function. So here it is now represent like that. So generally, a function is also known as a map or a mapping or a transformation or an operator. So now let us see some. So these are all about the definition of functions. So now, under which condition we can say that two functions are said to be equal? So here the conditions are very simple. If both the domain of the functions are exactly the same, and in the second condition we can say that if the functions are exactly produce the same output or same result, and that will be listed under the range of first function and range of second function, both are exactly the same, then we can say that yes, the functions are exactly same. So here two conditions must be satisfied, domain must be same, and the range set must be same. Along with we can say that the function or the engine or the transformation or the expression must also be same. Now here you can define a one function or injective function. So here the definition is quite simple. So we have represent like that when two elements A1 and A2 in the domain set are not equal, then their image are also not equal. Then under this condition, we can say that the function is a one or injective function. Now, onto function or surjective function. So here, the single condition is that when the range of a function is equal to its codomain, then the function is said to be an onto function or is also known as surjective function. Or in language form, we can say that for any element small b in capital B, that means element B in the codomain set, there must be an element A in the domain set such that we can represent f of A equals to f of B. If this condition satisfied for each and every element of the set in the domain, then we can say that the function must be onto function or surjective function. Now, the budgeted function. So whenever a function is defined from a set A to B and it satisfies both the condition of one and onto condition, then it is said to be budgetive condition or bijection or budgetive function. And whenever we define a particular function over a particular set, that is I is a function from capital S to capital A in the form of, and it is defined by I of A equals to A. That means input and output are exactly same. Then this kind of functions are known as identity function and represented by capital I. And here the bijective function always satisfy the properties of bijective. That means identity functions are always one function and onto function. Everybody join virtually. Okay. So is there anyone joining in my live class? Hello, can you hear me? So let us continue to discuss some more about the functions. So now a constant function will be now represented in the same form. Now f is a function from a to b, and you can represent if input is all the elements of the input set or domain set, and the result set or output set, output result will be always same, that is c, a constant. Then this kind of functions are known as a constant function. That means outputs are always exactly same for every input given to the function. Now let us know about the composition of function or composite function. So composition or composite of functions are possible when the range of the first function is the domain of the second function, or more generally we can represent like that. Now here we have taken here f is a function from capital A set to capital B set, and z is another function which is mapping from capital B set to capital C set, and these are two functions. And now we can define a composite function which is the composition of both the functions f and g function, and can be represented in the form of hx is equals to z fx inside bracket we can represent. So here we can clearly see that the range or the output of the function f is, again, it is the domain of input of the function z, and the same can be represented in the form of the Venn diagram as follows. Now here we can represent here the function, new function h is now called as a composition of two mapping two functions z and f, and is written as g composition f. And now in this picture or the diagram you can see clearly the first function f is from the set A to set B, and fx is the result or image of the element x from the set A. And here this fx is again defined by the variable y, which is the input element for the second function g, which is from the set B to set C. And finally, we can represent like that g composition f can be represented by a single function, and that is h. So here the same will be represented in the form of small o symbol. This small o symbol is also known as composition operator z o f inside bracket x. So x is the input of the function f. So these are some examples given on the compositions of functions, and these are basic elementary definitions of preliminaries about the functions. So here the actual definition. So let f is a function from a to b and g is a function from c to d. A two functions such that range of f is a subset of c. So here, then only you can say that the composition of z and f is possible, and you can represent the composition f is a function from a to d, and that will be defined by z or f of a equals to z f of a. The same idea has been explored with the following examples given in 14, 15, and 16. And again, there is an important result we will discuss. In this result, we will discuss about the injective and surjective composition condition of a composition functions. So here in this theorem number 1, f is given a function from a to b, and g is another function from c to d into functions, such that g composition f is a function defined from a to d. Then if g composition f is injective, then you can give a conclusion that the first function f is injective. Similarly, in the second statement, we can say that if G composition F is surjective, then so is that means the second function G from C to D is surjective. And these statements are proved by using the simple definitions of subjective and injective, which we'll discuss earlier in this session. Binary operation. So generally, binary operations are familiar to us, and we are using this binary operation from our school level. And basically, we are known about the algebraic operations like addition, subtraction, multiplication, division. All are interestingly these are known as the binary operations, which are operate over two numbers. So let us see exactly what is the basic definitions of binary operation, how we can represent, and what is the basic idea behind it. So here it has been written that a binary operation on a non-empty set S is a function from Cartesian product of the set itself to the set S itself. That means we can in language we can conclude that binary operation is a function whose domain is restricted to the Cartesian product of a particular non-empty set and which gives the output. The range is the set itself. So here are the some conditions which are represented like that. So when the binary conditions or binary functions or the function is defined in the form of binary operations, then this kind of conclusion can be made, and that has been defined in this definition. So here, or basically a binary operation is represented in the form of asterisk symbol, that means star symbol on the set S. And here, that binary operation is said to be closed on the subset E if the binary operations of first element T1 and T2, the result of this binary operation is again lying in the same set T, then we can say that yes, the relation or that means the function or the binary operation is closed or closure under the binary operation. Now, commutative property that is well known to us. Now, it can be represented like that S star B. That means binary operation of A and B is equals to the binary operation of B and A. If both gives us the same result, then we can say that the relation or the binary operation is commutative, satisfy the commutative law or commutative property. In the same way, we can represent the associative law S star D inside bracket then star C can be different like that A star B star C. So here this is the property of associative property. And here all the three elements A, B, C must be belongs to the same set S. Now can be present a distributive property over to binary operation. So here for distributive property we have taken two binary operations. One is small o, that is composition operator, and that is star. So basically the definition we are using these two notations as a binary operation which are operate on the set S. And we can say that or see here in the first condition of the property A star B O C, B composition C B O C. So here we can write A star B O A star C. So now in language you can say that the binary operator star is distributive over the binary operator O. In the other hand, we can also represent like that B O C inside bracket star A is same as to say B star A O C star A. That means here we can say that the same for the binary operation star is distributed over the binary operation O. So that means whenever we are dealing with two different binary operations which are different on the same set as, then we may adopt this principle of distributive property to deal with some algebraic calculations over the sets or functions. And some examples of binary operations are given. So here in this question, we have to show that this direct sum or this abstraction or this defined algebraic expression are really satisfy the binary operation, and we have to check the direction is distributive over delta in a set of real number form. So that is left as an exercise for the reader. So this is the summary of the second unit, which is dedicated to the functions and relations and their algebra or basic calculations of functions. Now the unit 3 is all about the coordinate systems and basics about coordinate geometry, and the fourth unit is dedicated to complex numbers. All basic about complex number. That means basically what is a complex number, how can we can represent a complex number like that. And finally, the last unit, the last unit is dedicated to the polynomial equations and their solutions. So here, as we have the idea about the polynomial equations, and in this preliminary idea, let us discuss about the quadratic equation. So here in quadratic equation, the general form or the common form, we can represent a quadratic equation or expression in the form quadratic polynomial like ax square plus bx plus c, where you can write here all the constant a, b, c may be any real number r, but here a cannot be as a not equals to 0. And this expression in polynomial form is known as quadratic polynomial, where the certain real number r in one variable x, because we are using one variable x. So when the same polynomial is equating to 0, then it will be known as a quadratic equation over the set of real number R, and that the standard form to represent a quadratic equation over a set of real number R. So now whenever I'm going to solve this quadratic equation, and we can get a solution, and the solution must be satisfying the same equation, and then we can look like that: a alpha square plus b alpha plus c equals to 0. And as we know, the roots of a quadratic equation can be calculated by using the simple formula, that is minus b plus minus under root b square minus 4ac all divided by 2 here. This particular expression or this particular formula is very much very useful to solve quadratic polynomials. And now the expression in this numerator under this square root b square minus 4ac is known as the discriminant of the quadratic equation x square plus bx plus c equals to 0. So now, as it is well known to us, when the solution of an equation is comes in complex form, then there must be other root which is must also in the form of its conjugate. That means whenever there is a complex root in an equation, then we have the other root, that is a conjugate, is also a root of this equation, and that has we can look there. So there are some examples given. Now the same idea has been extended to the polynomial degree n. So polynomial of degree n will be written with the form is written like that: a0 x to the power 0, a1 x to the power 1, a2 x square, dot dot dot, an x to the power n. So this kind of expression is known as polynomial of degree n. Condition is that an, the coefficient of the highest power of x, an, will not be 0. If n is not equal to 0, then we can say that this is a polynomial of degree n, and it will be represented by degree of and degree of f of x. So now when the degree will be 3, then it is clearly known as a cubic polynomial. When the degree is 4, it is known as biquadratic or quartic polynomials. Now let us note some fact about the polynomials. If f and g are two polynomials over the set of real number r, then their addition or subtraction will gives us a new result, and the degree of the new result or the output of the addition or subtraction of these two functions must be less than or equal to the maximum degree of the first polynomial or the second polynomial. In the same way, when we are going to multiply these two polynomials, is also a polynomial over R, and the degree of the result, the resultant polynomial, which was get after the multiplication, can we represent the addition of the degree of the both polynomials, first polynomial and second polynomial. Similarly, also we can represent the polynomial over complex number, polynomial over rational number. Now, when a particular element, when a particular element is a solution of a polynomial fx, then that particular value is known as the solution or root of the equation, or we can also say that is zero of the polynomial or the equation. So here a set of solutions of an equation is also known as solution set of an equation, because whenever we're going to solve quadratic equations or cubic equation, then we have exactly two or three depending upon the power of the equation. So if all the roots of the solutions will be represented inside the set, this set is known as the solution set of the polynomial of the equation of degree n. Now here we have listed that one. So we have considered here polynomial of degree n, and there is the equation form that is a0 plus 1 is a n into x to 1 is equal to 0, and here all the coefficients are the set of the real number r, and the highest degree coefficient is not equal to 0. Then you can see that yes, there are n roots in the set of complex number c, and all the roots can be written in the form of an into x minus x1 into x minus x2 into x minus x1 in the form of product of linear factors. So here, if alpha, beta, gamma are the three roots of the cubic equation x cubed plus b square plus cx plus b equal to 0 and equals to b, then we can clearly find that addition of all these individual roots must be by a, and the product of summation of product of pairs must be c by a, and product of all these roots must be known as b by a, and that can be represented in the form of the following form of coefficient of x square, coefficient of x, or coefficient of x to the power 0, that means constant terms. The same has been represented. So this this is all about the polynomial equations and their solutions. And today, this much from this counseling period of BMTC 131, which is all about the basic preliminaries of calculation. Stop କରିଦେଲି ହଁ ବନ୍ଦ କଲି ନା ରେକର୍ଡ ହେଉଛି ବୋଧେ ଦେଖିଲ ନା ପ୍ରେଜେଣ୍ଟେସନଟା ଷ୍ଟପ୍ କରିଛି ରେକର୍ଡ ହେଉଛି ବୋଧେ
ସେ